Hi guys, I hope you're doing well and staying safe. I'm going to be going over the Earth Structure and Systems PowerPoint that we went over earlier in the year, and hopefully this will help refresh your memory and potentially as you're taking some of the later tests, if you aren't sure about something, you can go back and review this, and hopefully it will help you. I'm also going to be breaking down each of the standards, and I will be going back and referring to some of the slides that are in this same PowerPoint. But this is a general overview, and hopefully you will enjoy remembering this. I'm going to click ahead. Uh, this is time in billions of years, and this is what the scientists believe at this point that the age of the Earth would be. And if you look, it's about 4.6 billion years old. And that's actually going to be one of the questions on your tests. It's going to be, what do scientists believe the age of the Earth to be? And, there is a lot of debate about that, and no one knows for sure, obviously. But the best guesses from the scientists and the Tennessee State Standards, they put in here 4.6 billion years. And in order to get a question right on a subsequent test, that's what you would put. Now, if you notice, the majority of this time is spent in the Precambrian. This is in a lot of the formative years of the Earth. And obviously, there are going to be more life forms on Earth today than there were originally because some of them have gone extinct. And you've studied about a lot of those in the past. I'm going to go back now to the previous slide. This highlights uh, the most recent times of Earth's age. If you will look at it and read the chart from left to right, the Cenozoic would be the time period that we are in right now. This is our particular era. This is the Cenozoic era. Previous to that was the Mesozoic era, and it was divided into periods called the Cretaceous, Jurassic, and Triassic. And a lot of you have seen the movie, The Jurassic Park, and so you can see that scientists believe that was a couple 100 million years ago. And as far as anything you put on the test, answers-wise, it would relate to this as well. If you go back into the Paleozoic time, before that, uh, this is where we get most of our fossils are from Paleozoic and the Mesozoic and then the Cenozoic time periods. The Precambrian time, there are very, very few fossils in that section. The geologic time scale, it showed that Precambrian time covered about 88% of Earth's history. If you remember the graph we just looked at, the majority of it, when it was broken down into billions of years, covered the Precambrian time. And there, as I said earlier, there are very few fossils from this time. The eras that we looked at, Cenozoic, Mesozoic, and Paleozoic, are the different eras that we are more familiar with. Obviously, we're going to have more research and more data, from those particular periods because they're closer to our time. I keep saying periods, but I meant eras. Periods are what each era is subdivided into. When I was talking about Triassic and Jurassic, those are periods within another era. The scientists believe that the moon was formed from a very early Earth, where it had collided with another object and a large chunk of it had knocked off and then created the moon. Now, this is, when you look at this, it says scientists hypothesize. And we talk about what is a hypothesis. Well, that's an educated guess. And so this is something that's not ever been proven true or false, but it's just their best guess at what may have helped create the moon. And this would mean that the Earth and the moon are close in age. Radioactive dating is what they used in order to come up with the 4.6 billion years. Obviously, they have no super way of testing that, but once again, this is their best guess. And when they looked at the rocks that were brought back from the moon, they realized they're about the same age as Earth. And so, in order, though we can't find an exact age, they do believe that the rocks dated to be about 4.6 billion years old. A lot of times when you are asked on a test the age of the Earth, some people put 4.6 million, but according to the Tennessee state standards, in order to get a question right related to this, you will need to put 4.6 billion years. Scientists think the Earth began as a ball of dust, rock, and ice in space, and gravity pulled all of this mass together. As Earth grew larger, its gravity increased, pulling more material into it. When these materials collided, it raised Earth's temperature. So you're going to ask yourself, well, how would it raise Earth's temperature? Well, when something hits something else, it's going to create a lot of friction as things slide by other things, and so you're going to get a lot of heat. And then they think that at that point the Earth melted. When it's all melted, the more dense material is going to sink and form the core. And this is basically the scientists' thoughts on this. It's hot, it's melted, the heavy things, the dense things are going to sink to the middle. And we know that our core is mainly iron and nickel, which are very, very dense materials. The less dense material then would rise and harden to form the crust and the mantle. Let me move myself real quick. All right, Earth's atmosphere formed next from the volcanic eruptions and collisions with comets. They think when a comet might have hit the Earth, it might have knocked some dust up into the air. As a matter of fact, some people believe that may have been a collision with Earth by some object that may have knocked so much dust and different debris into the air that it actually blocked out the sun and created an ice age. That's just one of the theories that's out there related to the ice age on Earth. But Earth's atmosphere formed from volcanic eruptions. That's where the volcanoes are spitting things up into the air, a lot of gases from inside the Earth. And these are going to float, obviously, up in the atmosphere. And the Earth being so hot, all the water is going to be a water vapor, and it's going to be up in the atmosphere. As Earth cools down, the water condensed into rain. Condensation is changing from a gas to a liquid, and it created the oceans. During early Precambrian time, much of Earth's rock cooled and hardened, creating continents. So why do we actually think this is true? Well, geologists have drilled holes as deep as 12.3 kilometers down into the Earth. Now, although that seems like a long way, if you think about people that run a 5K, that's a pretty good distance. And that's a little over 3 miles, about 3.1 miles. So this is actually, if you look at it, it's going to be um, quite a few miles deep into the earth. So trying to drill a hole that far is quite an extreme endeavor. But these drills have brought up samples of rock from deep within the earth, and that's one of the ways that we as scientists have determined what the earth's made of. Volcanic rock that's spewed up out of the volcanoes from inside the earth, those are also very useful into determining what's inside of the earth. And they therefore offer clues to Earth's structure and conditions deep inside the earth. There are also seismic waves from earthquakes. They also give us evidence. These waves are recorded, and geologists study how they travel through the earth. As we know, let me move myself once more. As we know, waves are going to travel faster through the more dense objects. Where particles are closer together, waves are going to travel faster. And although we think a lot of times about sound waves, we think the best way to hear them is through the air. But actually, in a gas, the particles are actually farther apart than they are in liquid or in solid. And so actually, if you think about sound waves, they travel faster through a solid than they do from a liquid, and they travel faster through a liquid than they do in the air. So when things are more dense, the waves are going to travel faster. And so seismic waves act a lot in the same way. The faster they travel, then we know, well, that must be a more dense area. But these waves are recorded, and geologists study how they travel through the earth. Not only do they determine the density of a particular area, they also tell where there is a change in the makeup of the earth. So if we look at the different levels of the earth, we think, well, how do we know that we're going from the crust into the mantle or from the mantle into the core? And that's because they are studying these seismic waves. And are they speeding up? Are they slowing down? And that gives us some evidence. I apologize for having to move my picture around several times, but this is just to help you. All right, once again, if we look at ocean waves, for an example, when they encounter something that's hard, and this is a way seismic waves may react as well, as waves encounter an object, they're going to curve around it. And so if we sense that there's some kind of a bending of those waves, then we realize that they've encountered something that's particularly hard in that area. A lot of people go out and use a metal detector or different things, or maybe a fish finder. You're out on the boat trying to figure out, is there a fish down here? Well, a lot of times it's just because it's sending down a wave, and if it encounters an object, then that's going to be identified on the screen. Okay, we look, and this is broken down compositionally and mechanically as to the layers of the earth. And in my class, a lot of times we talked about, well, when we were in the early grades, fourth grade or whatever, we learned about the structure of the earth, and we learned it in the compositional way. We learned, oh, well, there's a crust. And then we go down farther, then we're down into a mantle. And then if you go to the very, very bottom of the center of the earth, I don't want to say the bottom, but the center of the earth is going to be the core. And so the crust, mantle, and core is kind of how you would have learned it in the fourth grade or sometime in that period of your life. But there's also a mechanical way that we look at. And this is starts with the lithosphere. And if you look at the lithosphere, you notice it's larger than the crust. So the lithosphere is taking in the crust and the upper part of the mantle. And that's important because that's going to be a question that you're going to be asked on any kind of any Tennessee standard. What is the lithosphere? That's the crust and the upper mantle. Or it may ask you the opposite way. The crust and the upper mantle make up the lithosphere. Now, when they look at that, the lithosphere is composed of the continental crust. That's the part that we know where the continents are, where it's nice and hard up here that we can actually see. And then there's an oceanic crust as well, and that's the bottom of the ocean. Yes, that's liquid above it, but there's actually a crust that water of the ocean is sitting on. And then, as I had said earlier, the uppermost part of the mantle, and that's going to be incorporated in the lithosphere. Right below the lithosphere is the asthenosphere, and that's going to be a little bit different. That's a place where there's a lot of the rock cycle, a lot of the convection currents that we will be talking about in a little bit, where a lot of that takes place. Then you have the mesosphere, and that's the majority of the mantle. And then finally, we have the core. What you had learned as the core earlier now has been divided into a couple of other categories, the outer core and the inner core. And we're going to know that the inner core is going to be the most dense, and so the particles are going to be so tightly packed together. That's going to make up our inner core, and then the outer core is going to be a little more liquefied. Even though it's not going to be liquid, it's going to be more where the particles can move a little bit more. And that, as I said earlier, is going to be important as we talk on about our magnetic field. How deep have we dug into the crust? If you want to, you can pause the video at this point and click this and watch this. This is very interesting. It shows that, yes, we've dug a long way, but we've only gone about a third of the way through the crust. And this gives a lot of comparisons to, how far, how deep is the deepest um, well that's ever been dug by hand? What's the deepest swimming pool? And a lot of fun things that you would actually enjoy watching and maybe sharing with your parents as well. And then finally, we'll talk about how far we had dug at the the deepest holes, which have actually been surpassed, I think. But these are digging for natural gas or whatever. And the reason that they had to stop drilling was because the heat had increased so much the deeper they went that the bits would no longer work because they had overheated. And anybody that's ever used a chainsaw or used any type of cutting implement, when it gets hot, a lot of times it's not going to work as well at that point. But I do encourage you to pause this and watch that video at your convenience. Once again, I'll move myself. Next, as I was talking about the layers of the earth, as depth increases, so does the pressure and temperature inside the earth. Everybody knows if you've um, been in a swimming pool, decided to swim down very, very deep. Um, in the old days at the public pools, we had a 12-foot section. I don't think they get that deep anymore at a public pool. But I can remember as a young boy, trying to swim down and how the pressure would just destroy my ears the deeper I would go. And so um, that just makes a lot of common sense that the deeper you go, the more pressure there's going to be. And then also the temperature is going to increase. As you go down to the core, everyone knows that the core is super, super hot. So logic would tell us that the deeper we go into the earth, uh, and get closer to the core, then it's going to be warmer as we go down. I talked a little bit about the outer core being more liquid, and with the iron and the nickel moving around and rubbing against itself, a lot of scientists believe that this is responsible for Earth's magnetic field. Once again, we don't know for sure, and so the best that we can do is to make our best guess, which is called a hypothesis. Okay, this is an important section. This is about convection currents. And when we talk about convection currents, I want you to think about them in the forms of solids, liquids, and gases, and how this heat cycle from going hot to cold, back to hot to cold, hot to cold, that is going to affect the gas or the air. It's going to also do the same thing in the more solid areas down inside the earth and in water, and we're going to be able to look at those. But heat can be transferred in three ways: radiation, convection, and conduction. When you think about conduction, I want you to think about that as actually touching something. If you go to the stove eye and actually put your hand on the stove eye, you are touching it directly. And so there's a direct transfer of heat at that point. That heat from that stove eye is going into your body. This is conduction. And one interesting note that I will tell you is that the hottest portion is always going into the coldest portion. You're not going to have cold going into hot. When you touch something that's cold, you're going to think that that cold is going into your hands, but actually what is happening is the heat is rushing out of your body at a super fast rate going into that cold object, and it's warming it up. But what we sense as heat leaving our body, we call that being cold. And so that's always kind of interesting. Another way is through convection. If you had a pot of boiling water sitting on your stove, obviously if you put your hand in there, which I do not recommend, you're going to feel that heat in that liquid form. And that's also convection. Not only that, steam. as the steam and the water vapor begins to evaporate and to come out of that, if you put your hand over it, that steam is going to burn you as well. Once again, that is convection. And then radiation is where heat is actually traveling through empty space. That's why we feel the heat of the sun. There are not particles out there that heat is being carried by to us. That is actually just being transferred through waves. And so those waves are what we feel. We can feel that heat, and that is radiation. A lot of times you can feel this next to a campfire. If the fire's burning and you're standing kind of close, you can kind of feel that heat coming off of it. And that's radiation as well. And we'll talk about those things a little bit later. The density of material as it is cooled and heated is the driving force behind convection currents. So basically, I'm going to break this down into hot air rises. That's why we have hot air balloons. Hot air, when things are hot, they tend to spread out. I always talk about in class that back in the days when we actually had recess, kids would go outside when it was hot. They'd get out there and they'd run around and play. If it was warm, they would run. They would have a good time. But when it was cold and we would go out for recess, it seemed like all the kids would just huddle up kind of in little groups and they would try to stay close together. If you think about the penguins, the penguins are always cycling and they're staying close together. So particles act the same way. When it's super cold outside, those particles are going to try to get as close together. If they get together to the point that they all stick together, then they're going to be what we call frozen. But they're going to want to stay as close together as possible. And when you have more particles in a particular area, then that's going to mean more dense. So think about the kids on the playground that are huddled up because they're cold. On that one section of ground, they are going to be very, very dense in that area. That ground is really going to feel the weight of all of that, of all those students gathered in one spot. Whereas if the kids are out running around and there's a lot of space between them, the density will not be as much because there's not going to be as many particles in a given area. So we know that things that are heavy or dense are going to sink. And things, as they get lighter, they're going to rise. And so as we think about that, that works the same whether we're talking about gases like our atmosphere, or in the waters like in the ocean, or even down in the rock cycle. And so we'll be talking about those convection currents. All right, here is an illustration. Let me move myself real quick. Obviously, the blue arrows represent cooler areas, and the red is going to be the hot areas. And if you notice in this diagram of the Earth, that deep down inside the Earth where it's warmer, that's where the red arrows are, at the lowest point of that particular section. So as you see in the mantle, the red areas at the bottom of the mantle, you look up at the lithosphere, even though you can't see that, that's also a very, very thin layer in comparison to the Earth itself. And then the blue section the blue arrows are going to be the colder, more dense portions. So as we're talking about a rock cycle, if you look at the blue arrows, those blue arrows are going to be colder, so they are going to sink. The hotter areas, the red areas, they are going to rise. And that's going to create a cycle that moves around. Okay, I am going to stop at this point, and we will call this part one so that you're not totally overwhelmed, and it will give you an opportunity to rest and then maybe watch the next portion in just a little bit. Thank you very much.